Gentlemen, I now start our tech talk. Good morning. Have a good day. Whoever you are in the world, we are starting now our silicon carbide tech talk. Wide band gaps material is very, very important now. And articles in my magazine have paved the way for a while. And under the respect of Corona, I got the idea to use these articles in a tech talk to get engineers together with the companies and the authors. And we have for silicon carbide, Pete Losee from UnitedSiC, Kevin Speer, Mitch van Ochten for ROHM, and we got Yuan? Not yet, from Infineon. We were waiting for that member. And we have Jiri from STMicro. So we will start with the questions and see what the engineers from the field will bring up to us, and anybody who can contribute answers should just show and let me know. The first question I have here listed is, at what temperature can both wide bandgap materials, SiC and GaN, be used when most efficiently? Who want to start? Kevin?
Hi, Bodo. Yeah, thanks for the question. So at Microchip, our focus has really been on silicon carbide, although I think it may be a little more than a year ago, we have cooperated with Transform in developing a reference design supported by GaN power devices. So we do, as a company, continue to observe the wide bandgap developments. But so far today, we're offering silicon carbide. The question is about, I believe, Bodo, correct me if I'm wrong. The question is, at what temperatures can silicon carbide and GaN most efficiently operate?
Yeah,
just
make a statement to SiC. GaN was the previous session.
Sure. So for all of these devices, I think the limitation, well, for all of the wide bandgap devices, I should say, I think the primary limitation is not the semiconductor itself, it is the packaging techniques as well as the passives around the rest of the circuit. That actually creates the limiting point for operating temperature more so than the semiconductor device. If you look at just the semiconductor itself and the physics involved, the real parameter you're trying to follow there is the intrinsic carrier concentration. When junction temperature exceeds a certain value, the intrinsic carrier concentration, that is the number of free carriers available to conduct current, actually exceeds, and it exceeds the design doping concentration that you have in the device. And so you no longer have a device, you have a conductor at that point. So when you look at wide bandgap, silicon carbide, gallium nitride compared to silicon, that intrinsic carrier concentration stays quite low, all the way up to hundreds of degrees Celsius. So again, the real limiting factor is the packaging technology and the failure modes thereof, as well as some of the surrounding passive elements.
Any additional comments?
At ROHM, we rate all of our silicon carbide up to 175 degrees C junction temperature. which, as Kevin mentioned, is really a limitation from the packaging, not the silicon carbide itself. We do have another company who's using a different material for the package that sells the ROHM die with special packaging, good for 225 degrees C junction temperature. But I think, as Kevin said, the silicon carbide itself could exceed 300 C if the packaging would allow. Yeah,
I actually have tested in my past, and Pete knows what I'm talking about here. We have demonstrated functionality of devices, at 300 degrees C pretty easily. I recall earlier in my career manufacturing and testing devices at 500 degrees C and them operating just fine. But of course, these were not packaged components.
Yeah, I think I would echo that. Our parts also rated 175C. Packaging is got to sort of move up along with the junction temperatures. I mean, the core technology we have is around the silicon carbide JFET, where we've also had sort of R&D high temp IC programs where these can last reliably at 400C plus. So it's sort of the peripherals and packages. Of course, with our Casco technology, we have a co-packaged silicon MOSFET. Now that is a low voltage MOSFET, and we've run sort of reliability established at up to 200C, but that beyond that kind of boxes the Cascode in with the conventional low voltage silicon MOSFET. But if you think about practically using the devices beyond that kind of junction temperature, it's an entire system redesign kind of.
Thank you.
Maybe just short from ST side, I think there is a question: what is the efficient area, and what is the maximum temperature? So it was highlighted. Silicon carbide survive quite high temperatures. We have packages going to the 200 degrees Celsius. But if you look on the dependence of the RDS on versus temperature, it's relatively flat up to 7,500 degrees Celsius, and then starts to rise up for most of the products. And also, of course, the performance of the internal diode or the switching clauses in principle are rising with temperature. So by principle, the operation at low temperature, like 25 degrees Celsius or up to 100 degrees Celsius, are so-called best regarding the best performance. But then is a trade-off between the size of the heatsink and the heatsink system which customer is using. So this is also the point of the question. Thanks.
Thank you. I have another question listed here. We know that the voltage levels for GaN are in the range up to 1 kilovolt. And the question is, what voltage levels do they each have the greatest advantage? It's a question to SiC, and the question is, what voltage levels SiC should be recommended?
So maybe I'll start. This is Pete from UnitedSiC.
Okay, Pete.
So we've had 650 volt switches on the market for a couple of years now, and just have released our 4th generation 750 volt. It's a crowded space at 650, but we feel like 650 volt and up, the RDS-on specific advantages that silicon carbide can offer, and specifically silicon carbide JFET based technology can offer, really makes it a nice play at 650 volts and up. When you get to sort of the medium voltage space, after 3.3 kV, the question is, do you go with a single standalone unipolar device up to 10 kV, or do you start doing multi-level or series connection? This is sort of the question, but to us, 650 volt and up, is a good space for silicon carbide.
Yeah, thanks for framing that for us, Pete. I think a lot of the panelists here are going to have a similar track of thoughts. We really break this down by voltage class and application. And one thing that I think may be missing from the discussion and the broader community is the reason. And that reason is today's gallium nitride devices have to be grown on a dissimilar substrate. And what happens when you grow epitaxy to the device layers themselves on a dissimilar substrate is you get a lot of defects in the grown material. And that tends to, it doesn't kill the device, but certainly as part of the design, you have to make the device such that it allows margins to accommodate for the defectiveness of the device layer. So that's a real technology stopping point for GaN, and I know there are some GaN bulk crystal growth developments ongoing, but silicon carbide is probably 10, 12 years ahead of GaN in that aspect. So to circle back around to the question, where is GaN and silicon carbide best used? That problem that I just described is less impactful at the lower voltages than it is at the higher voltages. Again, kind of like Pete just said, as you go up to the medium voltages, 1700 volts, 3.3 kV and higher, I think silicon carbide and the silicon IGBT are going to be the real contenders there until someone can come up with a large diameter, low cost, high quality GaN substrate. And then even when that happens, we have to recall the superior thermal conductivity of silicon carbide as compared to GaN. In fact, the thermal conductivity of silicon is even higher than that of GaN. So even when they come up with this high quality, low cost, large diameter GaN substrate, there's still going to be some thermal challenges to face at the higher power levels. Be curious to hear what some of the other panelists think as well.
Thank you, Kevin. Then let's go to one of the incoming chats. Are you expecting some standardization of packages for SiC? Are existing packages such as TO247 well adapted to SiC, or are you expecting new packages becoming new standard?
I guess I could comment first on that, Bodo. ROHM has gotten a lot of mileage out of the TO247. We continue to offer the TO247, and about a year ago, we introduced the 4-lead version with the Kelvin connection, which significantly improves efficiencies at high frequency as far as the losses from switching. A lot of customers, though, prefer a surface mount package as opposed to a through hole. We did come out with a 7-lead surface mount package with Kelvin connection as well, but of course it's bottom cooled as most surface mount packages are, and we're getting requests from customers for top-sided or dual-sided cooling, so that is under investigation. The problem with the bottom side cooling is getting a sufficient heat sink connected to the package to really efficiently suck away that heat, whereas the top-sided cooling offers more options to extract the heat. So for the time being, the TO247 seems to be one of the major players for ROHM.
Yeah. I know that there are packages in development, and also that the historical bonding is under development, and that they have centered full spaces that gives more heat dissipation and better conduction. I do not know yet how far these are commercialized, but I think when that goes on, I expect the articles coming in to my magazine.
Yeah, this is Peter. I kind of would like to echo sort of the same sentiment as Mitch from Rome. The TO-47 we've seen to be sort of the workhorse. The 3 lead, sort of was the early sort of established package, but I think, over time, people see the benefits of this Kelvin source connection to get rid of the source inductance from the gate drive loop. So it really allows you to get more out of silicon carbide. But on the same token, right now I think we have a 9 milliohm 1200 volt 247 and a 7 milliohm 650 volt, and these are on resistances that before wide bandgap you just were unthinkable to put into TO leaded packages. So we kind of see the same evolution with surface mount obviously gets rid of a lot of those problems, but you got the thermal issues with the board mount. So top cool, double side cool, this kind of will be inevitably in everybody's roadmap, I think.
Yeah, and so far, gentlemen, Bodo, if I can, so far we've just been talking about discrete packages. I think a lot of the comments that Mitch and Pete are making about the TO-247, I think we can extend that as well into multi-chip power modules. Here again, the early packaging solutions are going to be based on what existed for the IGBT. So we think about half bridge modules, the 62 millimeter package, some of the, Infineon refers to them as the easy pack. These types of packages are available for some lower power applications. But in a similar way, the multi-chip power module packages are going to have to change a little bit from what IGBTs have been available in, because people are trying to take advantage of the high switching speeds made possible with silicon carbide. And if we're putting a high inductance IGBT package into this situation, bad things can happen, such as high transient voltage overshoots, sustained oscillations, EMI issues. So all these things can arise as well at the power module level. So I think the topside cooling is a trend for discrete packaging. The Kelvin source pin has been an enabler for discrete packaging. I think both of these things will hold true in the power module space as well, but we're all going to have to focus on lower inductance solutions for the power module space. Microchip does offer the SP6Li, which to my knowledge has the industry's lowest parasitic inductance at 2.9 nanohenries. So I think as a community, we're all going to have to get there, and we're all marching toward that new paradigm.
You see, looking to a TO-247 package is historically built on the tube socket. Tubes got replaced by TO-3 metal transistors in the same layout, and the TO-3 metal got replaced by TO-3 plastic, which is the TO-247. If you bend the leads, you fit into the TO-3 metal applications. So the TO-247 is a workhorse for decades, but the question is if this will continue into the future the way it did so far. So that's just a small comment from an old man like me. Gentlemen, I have another question there. Let me read it. We have seen 1200 volt SiC prices drop down to a level approaching range of GaN today at 650 volt. Which trend can you expect between the two technologies in the next decade? You can only mostly talk for the SiC devices. So, gentlemen, let me know your best. Price is always a physical dimension people look at because that enables the technical solutions. It needs always to be attractive to start doing something.
I mean, here I think I can give some comments on the projection of the silicon carbide cost down. For sure, it will continue drop without the technology improvement from the yield loss improvement, from the raw wafer coming down. And I think more and more applications with silicon carbide will steadily replace the silicon, like the superjunction applications. So this is definitely what we see within the years. More and more applications will go into the silicon carbide. That's what we can definitely already see from the performance and also the price down. Yep.
Thank you. Any additional comments?
Yeah, I mean, I guess I would just say that the trend is going to continue. The RDS-on cut is going to continue. The die shrink is going to continue. The packages are going to continue to get better. The number of wafer suppliers is increasing. The sort of capacity in fabs is increasing as both captive and foundry fabs realize the gains they can make by switching more and more to the line as silicon carbide pulls more and more. So I would say that this should be expected to be continuing.
Okay, thank you. The next question came in. It's about electric vehicle. Electric vehicle traction inverters will for sure be the biggest market opportunity for SiC going forward. Do you expect a spec standardization for SiC chips and packages to happen for automotive, or will customized solution see Tesla be the future? You see, when I when I introduced IGBTs in the mid-80s to Europe, and that went mostly into industrial areas, the question was always to have a second source. Otherwise, people hesitate to use IGBTs. Some strong people, they got forward and used the IGBT in the first step as a single source. I do not know how standardization can happen. What I remember on IGBTs, later on when the market had different vendors, they all had little different specific characteristics. So it was not easy a drop-in replacement between vendors. That's a question I think is addressed by that incoming node.
So, Bodo, if I can make a comment here, and hello, Marcus Biet. I recognize your name. I remember meeting you in the past, so I welcome this question. I want to start my comment with a bit of a story. So I think this was around 2013. I was visiting a major tier 1 supplier of EV traction inverters to OEMs, talking about silicon carbide and asking about their requirements. And early on in the conversation, the question was really quite simple. What are your DC link voltages and what voltage ratings would you like to see? And I qualified the question further by saying, so far what we're seeing is car manufacturers are using battery voltages of 400 volts or 800 volts. So which is it? So the response from these design engineers was, well, today we would like a 650 volt class device. I said, great. So I started taking notes down. He said, but before you finish writing that, as soon as you give us a 650 volt device, we're going to ask you for a 750 volt device. Oh, okay. So I'm scribbling that out, right? But wait a second, before you scribble that out, when you give us a 750 volt device, we're going to ask you for a 900 volt device. So this is a little bit funny, but it's also kind of a problem. And I think it ties in well to this question that Marcus has posed. Many of the OEMs are keeping these emerging disruptive type designs like Tesla has demonstrated close to the vest, and they're trying to do their own things. Meanwhile, they're sending suppliers like us, they're not giving us very clear information so far. We're taking on opportunities, and then we're finding out that the work we've taken on as part of that opportunity may not be applicable to some of the others. So I would love to see, and I've been preaching this gospel for a few years now, I would love to see some industry standardization in the xEV segment. I think that would help not just the suppliers of silicon carbide, but I think would help the users as well. Because then as a community, we're able to deliver more uniform solutions that more customers can use. The volumes go up, the prices come down, and more of the world can take advantage of silicon carbide technology. One man's opinion.
Thank you, Kevin.
This is Pete. I would say, dual sourcing or second sourcing and standardization are very different things. So these aren't interchangeable, right? And so while the OEMs or traction inverter folks are going to always make sure they have second source capability and they're not sort of holding on a supplier, we've not seen that there's sort of a real big need, at least in the early on, switch over towards standardization. Everybody has sort of really clever ways to get the most out of their wide bandgap based traction inverter. It seems from the sort of looks that we have, and so that I think at least in the near term this is going to continue. Different features of let's say the component level into the inverter, different packaging schemes, different thermal management solutions. So there doesn't seem to be evolving a standardization as of yet.
Thank you. I have another question here. Is there a package space advantage for SiC in terms of cooling requirements? I think the advantage to me is that SiC packages can be smaller and have a higher current rating versus silicon. The same can be stated for GaN. It's something common. I do not know if one of you want to comment more on that.
Well, the thermal conductivity of the silicon carbide is pretty similar to copper. So it's about as good as I think you're going to get. And so that does tend to help in getting the heat out of the part, but you still have the issue of getting it effectively into the coolant. But compared to silicon IGBTs, certainly the thermal conductivity of the silicon carbide is to your advantage. Not sure if that is exactly addressing his question or not.
Okay. There was another question. If there is a correlation between the use of SiC or GaN and the clock frequency for the inverter. I think it's a question to me what application the inverter is serving. motion control inverters have to have limitations based on the motor they drive. And I think it's not the device. That's what I know as an engineer. But I want to get your comments on that.
I mean, I think once you kind of look at switching, you know, the motor drive inverters over to wide bandgap, which are unipolar devices, you know, when you put together the loss tables, the switching losses, even, you know, slowing down the edge rates and switching at, you know, the 8 or up to 15 kilohertz that we see for these kind of like traction inverters, the switching losses are not the dominant percentage of the loss, right? It's conduction loss. And this is, you know, partially why there's a big advantage in sort of, let's say, light load efficiency, where, you know, the unipolar without a knee voltage of the silicon carbide switch is advantageous, right? So in many of these motor drive applications, conduction losses is key, knowing that, you know, your sort of switching loss is small in those frequencies. So, you know, this is one of the reasons why we actually go to our technology, which has a very low conduction loss, right? A very low RDSA with the cascode and silicon carbide JFET approach.
Maybe one comment for the high power solution, not only for motor drivers but also for the DC-DC converters like the chargers or the UPS systems. We see the customers can go to the frequencies with the silicon carbide up to 100 kilohertz, even above, depending if it works in the hard switching or soft switching operation. So here's definitely the move here, and you can reduce the size of the power parts. Why I'm not sure if again are at the moment so often used in this kind of the high power solutions where we talk about tens or hundreds of kilowatts. But for lower power, probably the frequency can go up to 1 megahertz, even for instance, 400 volt DC bus range.
And also, I think I would like to give some comments on the galvanic tracking 650 volts for like a telecommunication power supply, where the range is like 10 kilowatt. This range, for sure, the frequency will be go for much higher than silicon carbide due to the intrinsic benefit from physics, lower switching loss compared to silicon carbide again. So it can go much higher. And then for silicon carbide in drives, I think also the question is there's no need to go for that high switching frequency for motor drives. So basically, I don't know, 30, 20 kilohertz will be sufficient, and we do not see any benefit comparing with using GaN in this drive application already. Yeah.
Thank you. Here's a question coming in, asking again to the 247 package. And the question finally is, still inductive and handling overshoots requires creating or additional space for snappers. Modules cannot compete so far with pricing. It would be appreciated to come up with similar size SMT package, including electrical isolation, to avoid expensive DCB TIM. The question is, I remember in the 90s, there had been SMD versions of TO247. And I remember when I worked with the Swatch group, when they built inverters for the smart vehicle, they used our IGBTs. The next question here is about SiC models for SiC. Are they sufficient currently? It's a question to all of you.
Sufficient in terms of accuracy, sufficient in terms of having available models for all products. Not sure.
it's very open, the question. You see, as far as what I remember on SPICE models, you have to be very careful if they temperature compensated, and if they have the all kind of models. What I learned in my engineering life, it's limited how many and exact data you had for specification of the model used. And I think SPICE offers you different kind of accuracy based on what you put in. I remember when in the 90s, the University of Dresden did SPICE modeling based on the IGBTs we gave them. It was only a snapshot of the moment. If the next batch had a little bit shift, the SPICE model had to be adapted.
So maybe I can give a comment here on the SPICE model. I think Infineon also has SPICE model both for IGBT and the silicon carbide MOSFET. And technically, silicon carbide MOSFET SPICE model has, in general, higher accuracy in terms of simulation already compared to the IGBT, due to it's relatively simple to do the modeling compared to IGBT. So in here, for speed of the simulation with SPICE and accuracy, I would say for silicon carbide MOSFET, the SPICE is pretty good in this case developed compared to IGBT, and also all the simulation challenges there, like conversions, they are really getting better and better. So in a nutshell, it's somehow for simulation, the transient of switching and within the operation temperature range is pretty good. Of course, there's a lot of limitations. For instance, if you using SPICE to model transient, that is relatively hard because it's very hard to do the compensations exceeding the datasheet like the short circuit. I think then when you're using SPICE will have more errors. But in the normal operation, the SPICE model in MOSFET is pretty good.
Yeah, I think I would agree with Jiri's comments on the accuracy of the silicon carbide MOSFET SPICE models. Perhaps with a bit of exception on modeling the minority carrier dynamics around the body diode, especially at some of the elevated temperatures. But overall, I think the accuracy of today's models is quite strong. If I can, at the risk of derailing the question a bit, I think what may be missing a little bit more at this stage of the simulation game is simulation of EMI and parasitics effects. This is really quite a roadblock for the adoption of silicon carbide, not just the adoption of silicon carbide, but the adoption of it and extracting the performance benefits. To me, this is what's missing a bit from the community, and I know that others, including Microchip, are working on this as well. But yeah, back to the question, as far as the models available for silicon carbide power devices, like Zhihui said, I think they're quite sufficient from a terminal characteristic standpoint.
Just yesterday, Bodo, one of the competitor magazines, PSD, published an article about silicon carbide simulation using LT SPICE, which it's a very interesting article. They actually have some oscilloscope waveforms showing real world compared to the LT SPICE simulation. I would suggest if you have interest in seeing the accuracy of the model, take a look at that PSD article from yesterday.
Who generated it?
The power, I think it's Power System Design, PSD.
I will look at it.
Yeah.
No problem.
I can send you a link to the article. No problem.
That would be nice.
Okay.
I think I would just sort of cap off the question by saying same sort of statement that, you know, we have SPICE models. These are purely unipolar devices that operate in unipolar mode through all of their sort of recommended use. So they're typically good to better than 20%. You can kind of find all of those SPICE models. I think where the development is happening is sort of the out of SOA transients, like Zhihui said. You know, solid state breakers is an emerging, you know, application space for silicon carbide. And so, you know, getting through those sort of thermal transient and surge transients with an accurate electrothermal based model, this is challenging, and sort of we're going that as a, you know, developing these along the way.
Okay, gentlemen, let's continue to the next question. What do you think about SiC devices reliability, more specifically about gate oxide and body diode? What is the reason that some SiC suppliers provide SiC MOSFET modules with additional SiC diode in anti-parallel?
There are
go ahead.
There are some applications I call to mind, for example, the Formula E race car, where a significant amount of energy needed to be returned during braking back to the batteries, and the voltage drop across the body diode would be perhaps in the 4 volt vicinity at those high currents, whereas the anti-parallel diode was half of the voltage drop. So it made a significant difference in how much energy could be returned to the batteries.
Yeah, so if I can make a couple of comments as well. The question asked about silicon carbide reliability, specifically called out gate oxide integrity and body diode stability. So I think the first thing I would say is the gate oxide challenges that have faced the silicon carbide MOSFET are not something new. This is not unprecedented. You know, if we go back, and Bodo, I'm sure you know this as well as anybody. If you go back to the early 80s, the IGBT had some issues with the gate oxide reliability, and then even more so going back to the 70s, some of the early silicon MOSFETs did. These problems took a bit of time to diagnose, a little bit of time to solve, but they were solved. I would say the same thing has happened by and large for silicon carbide. Microchip, among others, is now reporting production grade MOSFET gate oxide lifetimes in excess of 100 years, and that's even at elevated temperature. So I think the concerns about the gate oxide integrity, I speak for Microchip here, and then I'll let the others weigh in on their devices, but I think this is a concern that is in the past. And I would say the same thing for the body diode, although this could be a bit unique to silicon carbide, just because of the energy levels that are introduced in the band gap as a result of the defects that are present that cause the body diode to degrade. So because of those energy levels that are introduced into the band gap, when there are minority carriers that recombine, that causes these defects to multiply and expand. And that's why we see the voltage drop across the body diode increase over time. This is going to happen no matter what in silicon carbide, unless the material quality is improved to the extent that these defects are no longer there. Again, if we go back to 2012, 2013, the presence of these defects that caused body diode degradation were everywhere. They were all over the materials. Today, this is no longer a problem. And again, this could vary from supplier to supplier, but Microchip has published quite a bit recently, in fact, showing that there is no body diode degradation whatsoever in our devices. So I think these two issues certainly are understandable for there to be concern from the community. But again, I would say these are not unprecedented, and these problems were solved in silicon MOSFET, silicon IGBTs, and we see that they're being solved in silicon carbide as well.
So I would just like
Thank
to
you,
add on
Kevin.
the body diode front, we often get this question since we use a cascode with silicon carbide JFET for our normally off FET. The question starts out with, does it have an integral diode, or do I need to use a separate antiparallel Schottky's? And the answer is it does. It actually does form a very good integral diode, because what we do, the low voltage silicon PN junction turns on with a low knee voltage, and it really doesn't contribute any stored minority charge because it's just a low voltage MOSFET. And then the JFET is conducting in the third quadrant through its channel, purely in unipolar mode. And so what you'll see is it's got a low knee voltage of only about 0.7 volts versus 2.5. But then the conduction it basically looks like a Schottky diode. And so, in the sort of, even if you're not doing sort of synchronous rectification while it's conducting through the body diode, there's no minority stored charge in the silicon carbide. So the bipolar degradation phenomena is essentially something that we kind of bypass with the integral structure of our body diode.
And if I can make one more point, kind of what Mitch was saying before, there are, and this goes back to the question too. I think the question asked about why some suppliers are offering modules with and without silicon carbide antiparallel diodes. Mitch made a point that the body diode at elevated temperature can sometimes see a voltage drop of about 4 volts. Well, if you put a diode in antiparallel to avoid the body diode from turning on, the critical point there is that the voltage drop across that Schottky diode compared to the voltage drop of the body diode. So you have to select a current rating of the Schottky such that the voltage drop is going to be lower than that of the body diode if you don't want that diode degradation to happen. So that is sort of an answer to why some suppliers are offering modules with and without body diodes. At Microchip, the body diode degradation phenomenon is not such an issue. Even so, we continue to offer both flavors just based on the customer's use case and their comfort level with this phenomena as well. But I think that's a really good point that Mitch makes, is it's not just so easy as slap an antiparallel diode on there and the problem goes away. You have to be careful that the voltage drops are of the right order of magnitude.
And I think also
Okay.
I just gave a short comments on the gate oxide reliability here. I think this is well known between all friends making silicon carbide, and it's also a matter of design trade-offs, what we see. And now we see more and more friends taking care gate oxide a bit more and more. And then the trade-off between the chip size and gate oxide reliability is also moving towards into more reliable gate oxide as the direction, what we see with the technology, RDSI improvement from the technology. So I think we see in the future that gate oxide reliability of the silicon carbide MOSFET will be more and more tackled and then improved.
Thank you, gentlemen. Let's move on. There were a couple of questions in the loop. Could you comment on the sickness which impact directly on RTH? As a matter of fact, we see various SiC die sicknesses from 100 to 300 μ for 1200 volt SiC MOSFETs. To me, we have seen that to conventional silicon MOSFETs, and it's a question for the thermal impedance at the end, as thinner as better is the thermal performance. That's what I remember from my days when I walked around and tried to help people optimize their design. Let me have your comments on that.
So I give some comments. I think for silicon carbide device itself or the material itself, the conductivity is very good as copper. So this leaves the whole contribution from the chips into the final backside. It's more coming from the solder layers. So then the improvement of the solder layers will significantly reduce the total RTH of the silicon carbide devices. So currently the soft soldering, I think here is the dominant part, and that's why I think Infineon having this new very thin layer of so-called .xt solder layer involved in the silicon carbide to further reduce the RTH from the chips into the backside, which we do see a great improvement by reducing the solder layer thickness and improve the performance of the solder layer instead of getting a little bit thicker or thinner of the chip itself.
So yeah, I'd like to just add to what Zhihui was saying. With the excellent properties of silicon carbide, it does play an advantage to thin the substrate, but the RDSAs of the chips are getting so low, as if, you know, for the example of our new generation of 750 volt JFETs, the substrate resistance itself is about 1/3 of the total on resistance of the device. And so, you know, we're chasing the thinner substrate from performance, not creating the heat as much or more so than the thermal conductivity benefit.
Okay, thank you. Let's go on. There is a short question. Thanks for asking the question. As a follow-up, how are the TCAD models today? I hope you got the correlation to the previous, I think, must correlate to the SPICE models. And I'm wondering what TCAD, computer aided design, was the shortens, which is common to me, but I like these shortened versions when they are not so common around. I hope you can, some of you can answer to that.
So I give a short comment on the TCAD simulation. I think this is more to simulate the device performance. It's not electrical performance. Once you design the structure of the MOSFET, and then you see what's kind of rule of thumb performance there. And then this is more development tool for silicon carbide or for semiconductors to before they produce the device. And
okay, that's on more to the back end in production than production and design, than in application and design.
Exactly, in front end
here. In front end. Okay, then let's go to the next. Could you comment on modest transconductance of SiC power MOSFETs, and how do you see improvements in future in terms of device design? Anybody can answer on the transconductance of future devices?
I think this question was addressed at Pete Losee, but if I'm right, Pete.
So yeah, in our cascode, we actually use a silicon MOSFET, so it's got high transconductance. To answer Kevin to the low transconductance of the silicon carbide MOSFET, I mean, you know, this pushes you to you know, either fundamental breakthroughs in the inversion mobility, which, you know, research keeps going on to try to advance that, or, you know, increasing channel density with finer pitch cells and even towards some folks walking towards even thinner oxides. So all of these have sort of some challenges associated with it, but you know, without really moving the needle on the inversion mobility, these are the sort of design tricks that you use. You know, this is sort of the pushing the brake, the sort of you know, the crossroads between when you sort of keep running down the planar DMOS like structure versus into trench MOS.
Yeah, didn't mean to put you on the spot there, Pete, but I think that's right. And by the way, I love talking to you, Pete, because we talk device stuff together. I think that's right. We have in the device design community, we have different knobs that we can turn. The thing is, when you turn one knob, the other one turns two. And I think that's sort of the point that Pete is trying to make. We have knobs and levers that we can turn until the point where the reliability trade-offs make it amenable to go to a trench type of architecture. Speaking from the Microchip vantage point, we don't believe we're at that inflection stage just yet. We still continue to think that the planar DMOS architecture is the more reliable choice. But you know, that's our standpoint, and I think we intend to stay that path for the foreseeable future.
Yeah, I would just jump on and say, you know, with our cascode-based approach with our trench JFET, you know, the trench JFET is a bulk transport device, which actually has high transconductance. So we kind of bypass the inversion mobility issue. And so now it sort of breaks some of those trade-offs, right? If we want to trade off, let's say, saturation current for longer short circuit capability, the penalty we have to pay for specific on resistance maybe is a little bit less than if we were sort of making that trade-off with a low transconductance device.
The last question is coming up. How do you think about SiC adaptation in high power traction such as railway, where now slow switching IGBTs support long cable lengths to the traction motors without filtering and damaging winding insulation? Let me make first a comment. And the motor is the limitation for the switching speed. And so, so far what I know, something must be done for the SiC switching device, if it's an IGBT or MOS, if it goes into railway. And we are in a quite higher voltage class. I know that the high-speed trains are using several kilovolt devices in SiC technology. That's just my comment in front. And now I want to have your final comment on that. There are not too many manufacturers doing traction devices.
So maybe from Infineon side, we do see the traction could be used for silicon carbide, and even though we still keep the slow switching, but due to the partial load efficiency, it is still technically or commercially interesting for silicon carbide apply in railway application. Of course, this is normally relatively conservative market, so the time and all the reliability testing and design will take a little bit longer time compared to the normal industrial, but it is in this direction for sure. And we have similar projects running on railway applications.
Thank you.